about audio? Can everyone hear me okay? Awesome.
Yeah, you're good.
We're good? Awesome. If we're good, then we will get started. Thank you so much. I see your message there. Awesome. Well, welcome back, everybody, to our second day of MOSI at the USF Engineering Expo. We're really excited to have you here. A quick introduction. My name is Catherine, and today is going to be all about technology that helps us see the universe around us, specifically telescopes. So we're going to talk a little bit about the history of telescopes, how telescopes work, and then we have a few fun activities that you can try at home involving telescopes. And at the very end, if we have time, we're going to give you a little taste of tomorrow by shooting off rockets, which are, of course, how telescopes get into space. So I am very excited to introduce to you all today. We have a special guest, an expert from our planetarium and our astronomy team, Mr. Jose.
Hello, hello. Well, thank you, Catherine, for that beautiful introduction. So yes, I work here at MOSI in the space department, and right now we're going to talk a little bit about telescopes. Now, in order for us to understand how telescopes work and what they do, it's important to understand their history. And it's also very important to understand the history before telescopes. So before this miraculous invention that has literally like skyrocketed our understanding of the universe, you used to go outside and look up at the night sky, and you just had to wonder, what are those little points of light? What are those planets? What are those stars? And you couldn't really get a nice view of them. You just had to use your eyesight. And that was it. You were limited to just using your eyes all the way up to about 1600 or so. And that's when Hans Lippershey, an optician, actually came up with a design for lenses. Now, lenses back in the day were actually somewhat small, and not nearly as well polished as what I'm holding here. But as you can see, if you look really closely through it, the lens actually allows you to kind of distort the image. And this one actually will flip the image. So as you can see my finger, this way, there you go. So as you can see my finger, it looks like it's upside down here. The lens, however, is a crucial element in one of the very first telescopes, which is called a refracting telescope. Now on this table here, I actually have an example of a modern day refracting telescope. As you can see, this one's fairly small, but the biggest part of the refractor is, of course, the objective lens right at the front. So I'm going to take the lens cap off, and you should be able to see a nice big lens in there. You might be able to see a couple of reflections, but again, the main purpose of that lens is just to kind of distort the image, because at the end of the day, this whole unit here actually functions to not just make the objects appear up close, but to give you a little bit more detail in what you're able to see. And again, this is just one of the examples of a refracting telescope. The reason it's called a refractor is because it uses those lenses. And those lens elements allow you to, again, bend the light and give you a nice, crisp, clear image. So refractors were invented and they were introduced. And in the year 1608, this wonderful guy called Galileo decided to take his refracting telescope that he built and point it up at the night sky. He was actually the first person whom we gave credit to actually point his telescope up at the cosmos. And that changed our understanding of the world completely. Not just the world, but our place in the universe. Now, his telescope was actually not the best in the world. In fact, it only really magnified the image about 3 times. That's it. So 3 times magnification. However, it did make faraway objects appear close. Then he tweaked his design a little bit. He was a great inventor after all. And he managed to get just about 20 times magnification. If you've ever used binoculars, most of them are right around 7 to 10 times magnification. So 20 times magnification for 1608, 1609 is actually kind of a big deal. But regardless, with that magnification, he managed to point it at one of these wandering points of light that seemed to kind of move around with relation to the stars. Those wandering points are actually the planets. And he pointed it at Jupiter, my all-time favorite planet, by the way. And what he saw changed our understanding completely. Not only did he see a large disk with some bands, And if you've ever looked at pictures of Jupiter, then hopefully you know what I'm talking about. But he noticed those bands, which are the equatorial cloud belts on the planet. And he also noticed 4 very bright but very present points of light around that object. And as he observed throughout the night, and throughout the weeks, and throughout the months, he noticed that each of those 4 points of light actually shifted, and they moved around the planet. Now, again, this is the 1600s, and that's actually when most people of the time thought that the Earth was, the center of our, not just solar system, but also of our universe. Because if you go outside on a dark, clear night, it does look like, the stars are moving around us. It does look like the planets are moving around us. And even in the daytime, it looks like it's the sun that moves around the Earth and things like that. But reality is that it's the sun that's at the center of our solar system. And again, looking at those moons orbiting another world really helped spark essentially the heliocentric theory of our solar system, which puts the sun at the center. So again, everybody thought the Earth was in the middle of our solar system, and then Galileo said, no, wait a minute. We've got this planet, and clearly these other objects are moving around it. They're not moving around the Earth, they're moving around this object. And if that's the case, maybe we're moving around the sun too, right? So it gave credence to the heliocentric theory, and like I said, our understanding of the universe has kind of grown exponentially since then. Now, telescopes were, again, used to make objects appear larger, to see things farther away, and that was very useful in military applications as well as navigation. So the telescope, the chronograph, all of those things helped us explore the New World much, much better. Now, let's go back to telescopes for a bit. So again, I've got this small refractor here, and it uses lenses, but there is a drawback to using lenses. The big drawback is that it's really hard and very difficult to make a good quality lens. And most of the smaller ones that are easily accessible to people like you or I, they're not the best quality lens. How does that affect what you see at night? It actually makes the image have what we call chromatic aberration or color fringing. You sometimes get this if you take a picture of a really bright, shiny object with a camera. You'll see this purple halo or like a blue or yellow ring around it. That's because not all wavelengths of light that, again, the lens is refracting or bending, not all of those wavelengths are coming to focus at this exact same point of light. And what that does is it causes those different colored wavelengths to be in focus if it's closer or in focus if it's farther away from the actual focal point. So a way around that, if you want a bigger, better quality telescope, is to actually move away from lenses if you still want to save money. And that's what brings us to the next type of telescope, at least for optical design, a reflecting telescope. Now, the Newtonian reflector, as it is most often known, was actually heavily used by Sir Isaac Newton, right? And essentially, it is a completely different optical terrain. Instead of using lens elements to refract or bend the light into focus, this guy right here actually uses mirrors to achieve the same task. So why don't we take a look inside? I'm going to, again, remove the lens cap here. There we go. And if you look inside, you should be able to see a very shiny object all the way at the bottom end of the tube. That shiny object is a mirror. Now, that mirror is not flat. It's actually curved, kind of like a soup bowl. So the light bounces off of the curved shape and it reflects, hence the name reflecting telescope. It reflects back to a smaller secondary mirror, which lives just behind this tiny piece that you see kind of poking out here. That's what we call the secondary mirror. And all it really is another angled mirror, but this time it is completely flat. And it's angled so that the light can bounce upwards through this draw tube, which is how you would focus the light by rolling in and out. And that's where your eye would go. So you would actually be able to look through a telescope just by looking through this piece here. Now, again, it's important for this telescope design to actually have that secondary mirror, because without it, all of that light bouncing from that soup bowl shaped mirror would be brought into focus somewhere in front of the telescope. And if you try to look at the light in focus, you kind of have to put your entire head in the way. And obviously that brings up a big problem because your head would be blocking all the light that's trying to get to the telescope. So Newtonian reflectors are actually very, very good at observing or resolving farther objects. So these are great for looking at things like planets. And again, it's because these don't use many lens elements. They just use mirrors to reflect light. And like I said before, mirrors are not as hard to make, really good, or really well, I should say, as a lens. So much more expensive to make a good lens than it is to make a good mirror. So this is actually a pretty sweet deal. Now, we've got the third main optical design, and this is called a catadioptric telescope. I know that's kind of a funky word, but this is essentially a hybrid, right? Like you've got some cars that run on gas, you've got some cars that run on electricity, and then you've got some cars that mostly run on electricity but have a little bit of a fuel reserve, and we call those hybrid vehicles. This is essentially a mix of both a reflecting and a refracting telescope. Now, what are some of the advantages of this? Well, as you can see, I don't know if you can see from the side. Here, let me turn it. If you can see from the side, this is a much smaller, much more compact design than something like this. Now, this would be far more challenging to fit in your car. And if you look at the opening, it's about 114 millimeters, which is roughly about 4.5 inches. The opening on this telescope is much larger. It's actually 235 millimeters, or 9.25 inches. And the bigger the opening, or the larger the lens, the more light you can gather, and therefore the more resolving power that you can have. So this is what will give you those nice, sharper images of faraway objects like the planets, or even if you're observing some double stars or nebulas, you want something that's kind of like this. So let's go through the design of the Schmidt-Cassegrain here. Now, this particular model of a catadioptric design, like I said, uses both types of elements. It uses mirrors and lenses. So if we look down the optical path here, you'll find that the light first passes through this lens here. This is actually what's known as the corrector plate. And I'll explain what that does in a little bit, but you could probably guess it corrects something, right? But as the light passes through, all the way at the very, very bottom, you once again see a nice, big, shiny object. That's our mirror, and it's also shaped like a soup bowl, right? So it's a nice concave mirror, and that bounces the light back to the focal point. Now, this is where we ran into a problem with our Newtonian reflector, where if you wanted to see the light at the front, you'd have to, block it with something. That's actually what this piece right here is doing. Behind this particular part is what we call the secondary mirror. And instead of being flat, this one's actually curved. This one's actually a convex mirror. And what that does is it kind of focuses the light back down the tube. And if you look real close on the camera there, you'll notice that at the center of this rear mirror, there's this black tower looking thing that's actually hollow. In fact, I should be able to remove a portion of the telescope, and you should be able to actually kind of see that it is hollow here. Now, it's okay. It's difficult to look straight down the scope, so I understand. However, that hollow tube is actually where your diagonal, you can see it better, is where your diagonal and eyepiece would go, and that's where you would actually focus the light. So let's talk a little bit about the actual lens element in here, because so far we've talked about the mirrors, and we kind of understood how that worked by talking about the reflector. But if we focus on the corrector plate, this actually has a very important job, because without this, the image from that convex mirror would actually be warped, right? It would be kind of like looking through a bubble. The image would be nice and bright, but it would look weird. It would be very distorted. So this lens, the corrector plate, actually kind of counters that by pre-warping the light that it sees. So at the end, you get a nice, crisp image that actually has a lot of detail because you got a lot of aperture here, a big, big opening. So it has a lot of detail, and you're able to resolve things much, much better and much easier. So out of the three, which one is my favorite? That's actually a really tough call because they each have their advantages. For example, the small refractor here, as you can see, is very small, very lightweight, and very easy to transport. You can actually safely move this one in a backpack and take it hiking, and maybe you can use it to observe some birds. You can use it to look at a faraway object. And of course, you can still use it for astronomy. So this one's really nice and lightweight and perfect if you want to travel with it. If you want a little more aperture, then you go for something kind of like this. The bigger opening here lets you gather more light, and so you're able to resolve finer detail. So this is going to give you better images on the planets, really nice, crisp, clean views of the moon, and things like that. But with that, you have the drawback of the size, right? This is almost as tall as I am right now, and it's not quite easily transportable. And then we come to the Schmidt-Cassegrain here, our catadioptric design, and obviously it's much more compact, but once you start pushing those apertures, in this case 9¼ inches or 235 millimeters, once you get nice and big openings, they start to get pretty heavy. Actually, putting it on this table, you have to lift like 45 to 50 pounds just to get it on the table. So it's still a little tough. But yeah, that's a brief history of how telescopes work. Now, telescopes here on Earth let you resolve a lot of really nice things, but they all succumb to Earth's atmosphere. Now, don't get me wrong. I love Earth's atmosphere, right? It gives us oxygen that we can breathe. It protects us from cosmic radiation that the sun gives off. So the atmosphere, perfect. However, when it comes to using telescopes, it's terrible because the atmosphere is in constant flux, right? You've got all these little water vapor, all the droplets, air currents, different air masses, different gases, nitrogen, all these things, and they each have a different temperature and a different density. So any light that's coming from space that's passing through, it's not passing through something like a nice, good lens. It's not going to be a clean transition. Instead, the light would kind of wiggle around. And the more it wiggles, the less sharp or the blurrier your image is going to be. And ultimately, it doesn't matter what size telescope you build here on Earth, if you don't have a way to compensate for that, you're gonna get some okay images. And that's the biggest reason why we actually have major observatories up on higher elevations where the atmosphere is thinner, so that we don't have to look through more of the atmosphere. So places like Hawaii, places like the Canary Islands, those are higher elevation, much bigger telescopes, and they all use essentially atmospheric diffraction computation, which is a whole advanced topic that I'm not going to get into. But the short version of it is they use a laser, and the machine knows that the laser should just look like a little point of light. And if that laser is wiggling around, it has the ability to actually shift the whole optical train to compensate for that in the opposite direction, so that your image stays nice and sharp. It doesn't appear to ebb and flow with the atmosphere. And again, that's building telescopes on Earth. You do have a limit, though. Building telescopes on Earth can limit you to only about 10 meters. That's actually our biggest observatory telescopes are just about 10 meters in size, because if we go any bigger, the mirrors would start to kind of flop, right? And that's why we've moved away from using a single very large mirror to using something like a series of smaller mirrors, and you'll see that later today. And we, of course, can only improve our telescopes on Earth if we put them beyond the Earth. If we forego the whole atmosphere, which will inevitably ruin our images if you want some precise detail. And that's where telescopes like the Hubble Space Telescope, come in really nice and clutch. Same thing with the James Webb Space Telescope, which we're going to be talking about later today. Hopefully it will launch on Halloween of this year, so that's exciting. Don't just look forward to candy, look forward to a nice telescope launch as well. And there's various other telescopes, each with their own design, since they're tuned for different wavelengths. But yeah, so a little history of telescope, a little bit of how they work. I'm going to go ahead and transfer it back to Catherine right now. So hopefully I didn't bore you guys with detail. But yeah, take it away, Catherine.
Yeah, no, thank you so much, Jose, for that wonderful introduction to telescopes.
You're very welcome.
To history and how they work. I really appreciate it. So now what we're going to do for the second half of our program is a few activities that you can try at home or if you're a teacher with your class. So the first one is building your own telescope at home. Jose showed us that one of the ways that a good refractive telescope can work is if you have two lenses. There's actually an apocryphal story, so we're not sure if it's true, that the inventor of the telescope actually got the idea from watching two of his children play with the eyeglasses in his shop and noticed that the weather vane further away appeared closer when they had two different lenses focused at just the right distance. So for this first activity, if you want to make a telescope at home, you're going to need two lenses. Now what I'm going to use today is two basic kind of cheap little magnifying glasses that I had lying around. You'll notice what's special about these is I have the little one here and I have the big one because you do need two different types of lenses. They cannot be the exact same. You could also do this with reading glasses, the ones that magnify things that are very small, not actual eyeglasses that see things far away. Or you can even buy these kinds of lenses online for not too expensive. You also need two rolls of either toilet paper tubes or paper towel tubes, something like that. And ideally, you need one that's smaller than the other. Mine are the same size. So my first step is going to be to cut one of them open. I've already decorated mine, which you can do yourself if you prefer. And I'm just going to cut one of them in half. So you need some scissors, some tape, and then have the other one kind of fit inside that, nestled very nicely. And I'll just tape the top of it here. Now you don't want to actually do what I did there and tape it to the inside because you're going to want to be able, once you have your spyglass, to kind of move the distance like so. That'll let you focus the lenses on whatever object you're looking at because it could be various distances away, right? So I am going to have my smaller lens, that little one there, on the inside of this tube. There we go. So I'm going to need my tape to be a little further out to accommodate that, or I can cut a little line. There we go. And it looks like I will need to cut a hole to make sure that that line is just right. So we'll cut a line there. And we will put it in. It ripped a little bit. That's okay. Yeah, so there's some finesse for sure with the crafting, but the basic premise is really, really simple. We just have two lenses, each affixed to one tube, and you're going to make a spyglass. So I'll cut a hole there. There we go. Perfect. You might need to make yours a little bigger. And I do already have one made that I can show you as well. I just thought it'd be fun to have a red one. So this is a really good little engineering project for you to try. So you can see now my lens is lined up kind of in the center of that tube. Okay. And once it's lined up, I will finish taping it all nicely. And then my second one is just going to be kind of affixed to the end. You could also cut a hole in it like I did here, so kind of make it fit as well, or you could just attach it to the end. Okay. So let me do that really quickly. Obviously, don't cover up your lens. And Jose talked a lot about the technical aspect and the specifics of these telescopes, but I really feel that building them is a really good way to kind of understand how they work. Even though this one is very, very simple, it gives you an idea for the bigger ones. Now, you can put them together and you can kind of adjust it like this. So you're looking through the small lens into the bigger lens. And mine right now is not focusing super well. So what I would have to do is make sure that that focal distance is correct. So I'm going to make mine smaller and put it in there. And now I can adjust it. All right, and it looks a little bit better. And you can test how far the distance should be the same way I did at the beginning, by holding them up like this and holding them apart until you have a rough focus. And that's roughly the distance you're going to need for your two lenses in order to get it right. And this one is just perfect. So I don't know if you can see into that. We can give it a shot. So I've got it through that little lens there, and then as I adjust, you see it? What's further away will appear clearer in that little lens, so I can see the door. And remember, like Jose said, this image is going to be flipped, so it's going to be inverted, remember? Just like when he did with his finger, and you could see that when you have it going up behind it, oops, oh, this one's perfect. Sometimes it'll make it look like it is going the opposite way. And you can adjust that by adding different amounts of lenses. So an even number of lenses is going to give you one image, and an odd number of lenses is going to give you a different kind of image. So there we go with that one. So that's one good activity that you can try at home to build your own telescope. The second activity that I wanted to show you is all about the James Webb Telescope. Mr. Jose kind of mentioned how that works. It's one of the telescopes that's going to be going into space, hopefully on October 31st on Halloween. And what's really cool about the James Webb Telescope is that they had to overcome a very difficult engineering problem. So Mr. Jose mentioned, the bigger the telescope, the more light it can absorb and the further it can resolve the image. So they wanted a really, really big telescope. But rockets are kind of small. They can only carry so much stuff. They're not going to be able to carry a giant, super big telescope into space. So they had to figure out how to overcome this challenge. And the solution they came up with was an origami kind of style telescope. So they had a bunch of different gold panels or coated mirrors here. And they had all these different hexagons. And the plan was that these hexagons would fold up, fit into the rocket, and then when it got into space, like origami, unfold, and then you would have a big telescope. So just to demonstrate that really quickly, I've got mine here, and I'm going to fold it in half, kind of give you an idea of what I'm talking about, and I'll fold it in half again. And I will fold it in half again one more time. And I need to create some sort of deployment system in order to get it to work. So I've got some string that's going to represent my deployment system. Let me get some longer, a bit longer. There's one, and there is two. Perfect. And now I will take them onto my telescope. And this is, of course, an oversimplification, but I hope it gives you a really good idea of how this telescope is going to work in space. So once they have that, they're going to fold it up. And they've got a rocket. We'll put their telescope into the rocket all safely. And they have some boosters that once it gets into space, here's our rocket. Ooh, it's in outer space. And now The deployment system engages and opens. Oops. Hopefully their deployment system does not come off of their telescope, and it will unfold. Oops, like so. Okay. So kind of a really novel solution. There's another cool telescope on Earth that employs almost the same idea. It has a bunch of smaller parts all over the globe, and a computer compiles those images together to make one giant image, almost like every individual telescope around the Earth is giving a few pixels, and then the computer program approximates the missing ones. So that's pretty cool. So we mentioned that rockets are a really good way to get telescopes into space, another important engineering challenge. And rockets are actually what we're going to be talking about all day tomorrow. So if you are somebody that prefers rockets to telescopes, please tune in. But we're going to give you a little taste of that right now. So I've got my little rocket here, 2-liter bottle, and let's go outside and launch it together. All right. This rocket is going to be propelled by water. It's going to use pressure to actually take off. We're going to use some kinetic energy there. Keep this door open. Welcome outside. We've already got our station set up. And I've got my bike pump that's going to give us a lot of pressure. And let's see. Okay. So the first thing I'm going to do with my rocket, oh, and you might notice up here at the top, I've got a little bit of foam and some Play-Doh tied on the top. That's because I want the center of mass of the rocket to be further up. Otherwise, it's not going to go quite as far. So first steps first, we'll fill up some water. And I only need to fill it up about a third of the way. A little slow going there. And the bigger your rocket, the further it's going to go with these kind of systems. But normally when you are sending a rocket, the more mass it has, the more fuel you're going to need. And thus, the more expensive it is going to be to launch that rocket. So every single kilogram of material that you send into space is going to cost you. So the lighter your rocket, the cheaper and easier it is going to be to send it into space, generally speaking. Okay, let that go. It should be good. A little more. I wonder if we have any future rocket scientists watching today. Okay. So, take that off. Make sure the water doesn't spill. I will get my launcher right here. Click it into place. There we go. Counterweights. I've got my little gauge here that tells me how much pressure I'm going to build up with my bike pump. Hopefully we don't lose our rocket today. Send it that way. Okay. Here we go. You can see the bubbles start to go. The more I pump, the less bubbles there will be, because there will be less room for all of that air, the more pressure I build up. I'm going to shoot for about 60 psi. I'm at 40 psi now. The more pressure, the harder it is to pump it up. All right, we're at about 55, 60. All right. I've got my launch mechanism here. I'm going to let our rocket go. Are you ready? Count down with me at home. 3, 2, 1. Blast off! Woo! Not bad, not bad. Very nice. Oh, I love it. Okay, let's head back inside. I have 2 review questions for you so that hopefully you can win an at-home science kit. All right, as we walk in, question number 1. Mr. Jose went over 2 main types of telescopes. What are they? What are those 2 types of telescopes called? Bonus points if you can get the 3rd type that he mentioned. We'll give you some time to answer that question. All right. Now that we're back, 2nd question. What is one of the major drawbacks to having a telescope on Earth as opposed to space? What's something that's going to hold our telescopes on Earth back a little bit compared to our telescopes in space? I'll give you time to answer that question. And remember, telescopes in space, while they might be a little bit better, they are harder to get to and fix. So that is a drawback. So pros and cons, right? All right. So we've talked about the history of telescopes. We've talked about the different types of telescopes that there are. We've talked about how those telescopes worked. We talked about how you can build your own telescope at home to kind of get a better idea of these physics principles. And we talked about some of the challenges to getting your telescope into space and how engineers have overcome them over time. I wanted to remind you as well that there's a very exciting astronomy event happening today. It is the landing of the Mars rover Perseverance. So that's going to happen Eastern Standard Time today around 4 p.m. So you can watch it live, and it's going to have 7 minutes of terror where it enters the Martian atmosphere, and we hope that all of our calculations and all of our math is correct, and that it'll land on the surface and not burn up in the Earth's atmosphere. So cross your fingers, watch it. It's going to be very, very exciting. It's years of work, and it'll hopefully give us a lot of new information about our planetary neighbor Mars. So very, very cool stuff. I want to open it up now in case you guys have any questions for me. We have a few minutes. I don't know if the chat feature is enabled right now. It is. Awesome. So go ahead and chat in the chat. Put any questions that you have, and I or Mr. Jose or one of our other MOSI people behind the screen will attempt to answer those questions. Do we have any yet?
We had one comment from Kyle that says Earth's atmosphere or its weight.
Oh, that was the answer to my question. Yes. Good. I'm not sure if I'm supposed to give the answers if it's a contest. But yeah. Okay. Good.
No other questions.
No other questions? All right. If you don't have any other questions, or if you think of any questions later, feel free to reach out to us. We are on Facebook at MOSI in Motion. We are on Instagram at MOSI in Motion. We're also on TikTok at MOSI Tampa. So anywhere you can find us, shoot us an email. We are happy to answer any of your science questions. Thank you for attending our session today, and we really hope to see you tomorrow all about rockets. It's going to be a great time. It's going to be a blast. See you later.